Okay, I wanted to talk to you guys about this problem on your Gibbs free energy worksheet and kind of give you a method for evaluating problems like this. This is probably one of your more challenging problems to figure out, but the best way to do this is to visualize it on a line. So let's read through this together. If you haven't tried this one, two crystalline forms of white phosphorus are known. Both forms contain P4 molecules, but the molecules are packed together in different ways. The alpha form, that's this one right here, is always obtained when the liquid freezes. So it goes from liquid to solid, we're going to have all alpha. However, below a negative 76.9 degrees Celsius, the alpha form spontaneously converts to the beta form. What does that mean? That means this process, alpha converting to beta, is spontaneous below negative 76.9 degrees Celsius. And just from that information, you can categorize this reaction as one of our reactions in this little table up here. It's one that is spontaneous at low temperatures. And if you find that in the table, it's this one right here. Which means we can see what our two values must be here to be spontaneous at low temperatures. To diagram that, though, if you're not wrapping your mind around that, and how would you figure that out on your own? To diagram this problem, it looks something like this. I would put a temperature line, and this would be our freezing point. So above this temperature, we are all liquid. Below this temperature, we're all solid. So as we go this direction, we're all solid. And the first solid that forms is the alpha solid. So I'm going to write P4, and I'll do our alpha symbol for that. So we're all P4 alpha. This is also a process that is spontaneous only at low temperatures. So you could write the equation, I'll write it up here, P4 liquid going into P4 alpha is spontaneous only at low temperatures. But the one that we're caring about is the alpha going to beta. So we're going to keep cooling this off, and at a point of negative 76.9 degrees Celsius, this process becomes spontaneous, and as we cross this threshold here, we start to produce predominantly P4 beta, which means this process, alpha to beta, is spontaneous at low temperatures. So we're spontaneous over here, and the process would be non-spontaneous. I'll just do in S for non-spontaneous on this side. That means if you look at this little equation here, delta G, Gibbs free energy, being delta H minus T times delta S, if we want to evaluate this and try to make our signs so that we're spontaneous at low temperatures, I want a negative over here when temperatures are small, when this value is small, and a positive when temperatures are large. Well, when this is small, if this is a really small number, think of 0, the smallest number. That means this number here needs to be negative. And if I want delta G to be positive at high temperatures, I already determined that delta S should be a negative. If I want this to be positive at high temperatures, well, a high temperature, this term right here is going to get large. And a negative minus, if this was positive, would just get me more and more negative. I want it to be positive, so we need to have a negative number here so that my negative minus my negative adds, and we can get a positive value here. And so both delta H and delta S have to be negative. That's how you'd evaluate this problem. If you weren't given information about the actual values for delta H and delta S, you're just given information about spontaneity at different temperatures. What does that mean for this temperature here? Well, at this temperature, we're at equilibrium. And what is Gibbs free energy at equilibrium? Well, Gibbs free energy here would be equal to 0. And if you plugged it into this equation, you get a value of 0 here. Okay? That's where Q would be equal to K. So I wanted to walk you guys through this particular problem on your worksheet. The other ones should be pretty straightforward. Ask me questions if you have any, and I'd be glad to answer them.